Welcome to this session of the class, today's class. So, we will be talking about a 4-dimensional parabolic and linear partial differential equation. So, it is basically 3-dimensional in space, 1-dimensional in time. So, it is a 3-dimensional transient heat conduction problem. So, the governing equation will be in general looking something like this: del u del t is equal to del square u del x square plus del square u del y square plus del square u del z square. Now, we formulate a well posed problem and a basic problem, that is at time t is equal to 0, u is not equal to 0, let us say u is equal to u naught, and the other 6 boundary conditions, we need to have 2 conditions specified on x, 2 conditions on y, 2 conditions on z. So, all of them are Dirichlet, let us say at x is equal to 0 and at x is equal to 1, we have u is equal to 0, at x is equal at y is equal to 0 and y is equal to 1, we have let us say u is equal to 0, at z is equal to 0 and at z is equal to 1, we have u is equal to 0. So, let us say all the 6 boundary conditions are homogeneous and the initial condition is non-homogeneous, though. So, this is a well posed problem. Now, in order to solve this problem, since this operator is a linear operator and all the boundary conditions are homogeneous, we can use separation of variable type of solution safely. So, if we solve, we consider that u is constituted by product of 4 factors. So, this is u is a function of x, y, z and t. So, it is a product of 4 functions, which is a function of time alone, another is a function of x alone, another is function of y alone, another is function of z alone. So, therefore, we substitute this equation into the governing equation, it will be getting x y z dt dt is equal to x, okay, we will be getting z y t d square x dx square plus z x t d square y dy square plus x y t d square z dz square. So, we divide both side by x y z t, what we will be getting is that 1 over t dt by dt is equal to 1 over x d square x dx square plus 1 over y d square y dy square plus 1 over z d square z dz square. Now, if you look into this equation, the left hand side is a function of time alone, the right hand side is a function of space, and they are equal, they will be equal to some constant. If this constant is 0 and positive, we will be getting a trivial solution. So, this constant has to be a negative constant. So, this becomes minus lambda square. Now, we will be formulating the x containing part. So, that we move y and z to the other side. So, this becomes 1 over x d square x dx square is equal to minus lambda square minus 1 over y d square y dy square minus 1 over z d square z dz square. Now, again the left hand side is a function of x alone, the right hand side is a function of y and z only, and they are equal, again they will be equal to some constant. Let us say this constant if this constant is 0 and positive, you will be getting a trivial solution, that is not allowed. So, therefore, this constant has to be a negative constant. Let us put it as minus alpha square. So, we will be getting the governing equation of x, d square x dx square plus alpha square x is equal to 0. Now, the x containing part must satisfy the boundary condition of on x boundaries of the original problem. So, therefore, at x is equal to 0, capital X is equal to 0, and at x is equal to 1, capital X is equal to 0. So, that was those are the boundary condition of the original problem. So, x varying part must be satisfying that. Now, if you look into this equation is again a standard eigenvalue problem, and both the boundary conditions are homogeneous and they are Dirichlet. So, we have already seen the solution of this problem. The solutions are the eigenvalues are given by n pi and eigen functions are given by sin n pi x. So, therefore, alpha n for this particular problem is equal to n pi, where the index 1 n runs from 1 to 3 up to infinity. These are the eigenvalues, and eigen functions are given by x n is equal to C 1 sin alpha n x, that means C 1 n pi x. Now, let us look into the other two parts, minus lambda square minus 1 over y d square y dy square minus 1 over z d square z dz square is equal to minus alpha square. So, therefore, we take it as minus, we take it on the other side. So, 1 over y d square y dy square should be minus lambda square plus alpha square minus 1 over z d square z dz square. Now, this the left hand side is completely a function of y, the right hand side, these two are constants, the right hand side is completely a function of z, they are equal and they will be equal to some constant, let us say this is minus beta square. This constant can be positive, this constant can be negative, this constant can be 0. If it is 0 and positive, this constant, then we will be getting a trivial solution. So, this constant has to be a negative constant. So, we will be getting d square y dy square plus beta square y is equal to 0, subject to the boundary conditions. Now, we formulate the boundary conditions of y. We have already seen that the boundary conditions of the original problems at y are homogeneous. So, therefore, the y varying part must be satisfying the boundary condition of the original problem in the at y boundaries. So, therefore, at y is equal to 0, we have capital Y is equal to 0, at y is equal to 1, we have capital Y is equal to 0, and if you look into this problem, this is again a standard eigenvalue problem and the homogeneous Dirichlet boundary condition. So, the solution to this, so beta m r is equal to m pi, where m is equal to 1, 2, 3 up to infinity. They are the eigenvalues and eigen functions will be composed of y is equal to some constant C 2 sin beta m y. So, m pi y. So, these are the eigen functions. Okay. So, next we look into the z varying part. If we look into the z varying part, this becomes minus lambda square plus alpha square minus 1 over z d square z dz square is equal to minus beta square is equal to 1 over z d square z dz square is on the other side. So, bring it to the other side minus lambda square plus alpha square plus beta square. So, again this is a combination of the constant. This constant can be 0 if this constant is 0 and positive, we are going to get a trivial solution. So, this constant has to be a negative constant, let us say it is nu square. So, d square z dz square plus nu square z must be equal to 0. Now, we get the boundary conditions on z. The boundary condition of the original problem were Dirichlet homogeneous. So, boundary conditions on z should be again Dirichlet homogeneous on the z boundaries. So, at z equal to small z equal to 0, capital Z is equal to 0, at small z is equal to 1, capital Z must be equal to 0. So, again we see this is a typical standard eigenvalue problem with 0 initial 0 homogeneous boundary conditions. Now, the eigenvalues of this problem is known and the eigenvalues are again given by p pi and eigenfunctions are sine functions sin p pi z. So, therefore, we will be getting the eigenvalues as nu p is equal to p pi, where p is equal to 1, 2, 3 up to infinity, and eigen functions or solutions are z p, where this will be C 3 sin p pi z. Okay. So, these are the eigen functions, and now what is left is the time varying part, but before going into the time varying part, let us examine what this equation means. This equation means that minus lambda square plus alpha square plus beta square is equal to minus nu square. So, therefore, lambda square you just take it, just change over the sign. So, lambda square is nothing but alpha square plus beta square plus nu square. So, if you put values of alpha, so these are n square pi square, value of beta this is m square pi square, value of gamma that is p square pi square. So, we put a subscript lambda m n p. So, this becomes m square plus n square plus p square pi square lambda square. So, the time varying part, we will look into the time varying part 1 over t dt dt is equal to minus lambda m n p square. So, corresponding to the m n p, the corresponding solution we will be also getting m n p, we write it m n and p. So, lambda square is given by all this in as a function of m n and p. So, therefore, the solution to this time varying part is known to us m n p, function of time will be exponential minus lambda square t, and where the lambda values are already known from the value of m n p and pi square. So, we will be getting the complete solution by simply multiplying both all the 4 solutions of the sub problems. So, u m n p as a function of x, y, z and t becomes it should be multiplied by. So, it should be multiplied by t m n p multiplied by x n multiplied by y m multiplied by z p. So, we will be able to get the complete solution as u becomes summation of u m n p. So, 1 summation is over m 1 to infinity, another summation is over n 1 to infinity, another summation over p 1 to infinity. So, u as a function of x, y, z and t, this becomes triple summation m is equal to 1, n is equal to 1, p is equal to 1 to infinity, and this will be, you multiply all the constants. Okay. The solution of t should be associated with a constant C4. So, we multiply all the constants, all the functions. So, it will be having a new constant, multiplication of all the constants C1, C2, C3 and C4. So, you will be having C m n p exponential minus lambda m n p square times t sin n pi x sin m pi y sin p pi z. So, that constitutes the complete solution. Now, the constant C m n p has to be evaluated. For that we utilize the initial condition. The initial condition was at t is equal to 0, u was equal to u naught, and we will be using the orthogonal property of the eigenfunctions or the sine function. So, we multiply both side by sin m pi x, sin n pi y and sin let us say q pi z. So, and dx dy dz and integrate over the domain of x y z. So, it will be u naught, okay, we will just write it first 3 summation, one is over m, another is over n, another is over p, c m n p, it will be 1 sin n pi x sin m pi y sin p pi z. So, we multiply both side by all this. So, it will be triple integral 1 over from x is equal to 0 to 1, another over y, another over z. So, it will be u 0 dx dy dz. This will be triple summation C m n p integral sin n pi x. Okay, it should be multiplied by sin all this. So, I will just write, this will not be, I will just write it on the next page. So, that will be more convenient. So, it will be u 0 is constant, it will be taken out. So, this will be 1 over x from 0 to 1 y z sin m pi x sin n pi y sin q pi z dx dy dz, and this in the on the right hand side it will be triple integral m n and p c m n p integral sin n pi x sin m pi x dx from 0 to 1, one more integral 0 to 1 sin n pi y sin m pi y dy, another will be on sin p pi z sin q pi z dz from 0 to 1. Now, we utilize the orthogonal property of the sine function and open up the summation series. If you really do that, then all the terms except m is equal to n, they will vanish, and except m is equal to n and p equal to q, they will vanish. So, whatever is remaining is the one term c m n p 0 to 1 sin square n pi x dx 0 to 1 sin square n pi y dy and 0 to 1 sin square p pi z dz. Now, value of this is half, that we have already seen, half each. So, it will be 1 by 2, 1 by 2, 1 by 2. So, it will be 1 by 8. So, it will be C m n p divided by 8, and let us look what is the value in the of this on the left hand side. So, C m n p divided by 8 should be is equal to u naught integral sin m pi x dx 0 to 1 integral 0 to 1 sin n pi y dy 0 to 1 sin q pi z dz from 0 to 1. We have already seen this one. This is nothing but 1 minus cosine m pi divided by m pi. This will be 1 minus cosine n pi divided by n pi, and this will be 1 minus cosine q pi divided by q pi. Now, we change the running index, change index q to pi, q to p. So, everything will be m n p. So, you will be getting C m n p is nothing but 8 u 0 divided by m n pi cube m n cube pi cube 1 minus cosine m pi 1 minus cosine n pi 1 minus cosine, this p should be changed to q should be changed to p cosine p pi. So, the complete solution will be evaluated as u 0 u as a function of x y z t as triple summation over m n and p. This becomes 8 u naught divided by m n p pi cube 1 minus cosine m pi 1 minus cosine n pi 1 minus cosine p pi e to the power minus lambda m n p square times t sin n pi x sin m pi y sin p pi z. Now, this gives the complete solution of a 4-dimensional problem, and by looking into the values of u naught, we can really compute the compute the profile of u as a function of x, y, z and t. And we already know what is lambda m n p is, that lambda m n p square is nothing but pi square bracket m square plus n square plus p square. Now, if you see a typical sequence of things whatever we have done, that if we have a one dimensional, if we have a let us say types of problem and nature of solution, if it is a 2-dimensional problem, that is one dimensional in time, one dimensional in space, we will be getting one summation in the solution. If you have a 3-dimensional problem, then one dimension in time and 2-dimensional in space, then we have 2 summations in solution. If you have a 4-dimensional problem, one dimensional in time and 3-dimensional in space, then you have 3 summations appearing in the solution. Now, in case of one summation, it is in case of 2-dimensional problem, you are doing one integral is appearing on the left hand side to evaluate the final constant. For 2 summation, 2 integrals, that means double integral appears to evaluate the final constant. In case of 3 summation, we will be having 3 integrals or triple integral appears on to evaluate the final solution. So, you just see the sequence of the nature of the solution changes, how the variation of the problem they differ. For a 2-dimensional problem, we will be having 1 summation in the final solution. For a 3-dimensional problem, we will be having 2 summations. For the 4-dimensional problem, we will be having 3 summation series, and we will be having 1 integral, 2 integral and 3 integrals, double and triple integral to evaluate the final constant. Okay. So, if as we have seen in the earlier case, that depending on the solution on the nature of the boundary condition of the even for the multidimensional problem, the eigenvalues and eigenfunctions will keep on changing. That means, in the earlier problem we have considered that all the boundary conditions are Dirichlet boundary conditions. If one of the boundary condition, let us say on y direction, the boundary condition at let us say y is equal to the boundary condition at y is equal to 0 becomes a Neumann boundary conditions. That means, it is insulated at that particular wall, or there will be constant heat flux at that particular surface or boundary. Then we will be having a Neumann boundary condition, and all the other boundary conditions are Dirichlet type. Then the eigenfunctions for x will be sine functions, eigenfunctions of y will be cosine functions, and eigenfunctions of z will be sine functions. If all the boundary conditions are homogeneous and Dirichlet, but one of the boundary conditions at z, let us say z equal to 0, it becomes a Neumann. Then the eigenfunctions for x will be sine functions, eigenfunctions of y will be the sine functions, but eigenfunctions of z will be the cosine function. If the if the boundary condition on y, let us say it becomes a Robin mix at x is equal to at y is equal to 1, then eigenfunctions will become sine functions, but the eigenvalues will be no longer n pi in this case. The eigenvalues will be obtained by the transcendental equation, that alpha n tan alpha beta m tan beta m plus some constant, let us say Biot number or some constant, those will be appearing in the governing equation should be equal to 0. The roots of these transcendental equations will become the eigenvalues. So, therefore, depending on the nature of the boundaries, the eigenvalues and eigenfunctions will be done appropriately. Similarly, if you have the typical for a typical problem where you will be having all sorts of non-homogeneities appearing in the boundary conditions, then we have to make the problem non-dimensional such that at least one non-homogeneity will be reduced, let us say from 5 to 4. Then this problem has to be divided into 4 sub problems considering one non-homogeneity at a time, and this problem has to be solved completely by breaking down into sub problems considering one non-homogeneity at a time. But out of these 4 sub problems, one sub problem will be well posed, because it will be containing a non-zero or non-homogeneous initial condition, but homogeneous boundary conditions. So, that problem will be a well posed problem, and that will be completely solved the way we have solved this problem just earlier. But all the other problems, all the other 3 problems will be ill-posed problem because the initial condition becomes homogeneous, but at least one boundary condition becomes non-homogeneous. So, each such sub problem will be again divided into two sub problems. One will be time dependent part, another will be time independent part. The non-homogeneous boundary condition will be associated with the boundary condition of the time independent part or the steady state part. So, by doing that, you force the boundary condition appearing in the time varying part to be homogeneous. So, we will be having, and the initial condition of the time varying part becomes will become the solution of the steady state part with a negative sign. So, therefore, the transient problem becomes a well posed problem, it becomes a non-homogeneous initial condition, and all the 6 boundary conditions becomes homogeneous. So, that becomes a well posed problem. We have seen how to solve that problem several times in earlier classes. So, after solving all these 4 sub problems and then add up all the solutions, we will be getting the overall solution of this 4-dimensional problem. Now, one may be wondering that if we have the boundary conditions, we have looked into all kinds of boundary conditions, but there are certain things one has to check that I will just list it down. Boundary conditions, and nature of eigenvalues and eigenfunctions. This is Dirichlet boundary condition at x is equal to 0, u is equal to 0, at x is equal to 1, u is equal to 0. So, these boundary conditions are Dirichlet boundary condition. The eigenvalues were n pi and eigenfunctions were sin n pi x. Now, at x is equal to 0, del u del x is equal to 0, and at x is equal to 1, u is equal to 0. So, this becomes Neumann boundary condition, this becomes a Dirichlet boundary condition. The eigenvalues are 2n minus 1, pi by 2, and sine and cosine functions are the eigenfunctions. Cosine 2n minus 1 pi by 2 x are the eigenfunctions, and at x is equal to 0, if you have u is equal to 0, and at x is equal to 1, if you have del u del x plus beta u is equal to 0. So, you will be having a Dirichlet boundary condition here, you will be having a Robin mixed boundary condition at this boundary. Then eigenfunctions are roots of the transcendental equation tan alpha n plus beta is equal to 0, and these are the eigenvalues roots of the transcendental equation alpha n tan alpha n plus beta equal to 0, and eigenfunctions are sin alpha n x. Okay. Now, the point is, if this boundary condition is reversed, will the same thing will take place. Now, that means instead of Dirichlet boundary condition, there is no problem. Instead of Neumann boundary condition and Dirichlet boundary condition, instead of x is equal to 1, if we have a Dirichlet boundary condition at x equal to 0, that means x equal to 0, I have u is equal to 0, and this Neumann boundary condition becomes at x is equal to 1. That means at x is equal to 1, del u del x is equal to 0. Similarly, in this case, at x is equal to 0, u is equal to 0, we put it the other way around, we just interchange the boundary conditions. At x is equal to 0, we put del u del x plus beta u is equal to 0, and at x is equal to 1, we have a Dirichlet boundary condition. So, what happens when these boundary conditions are interchanged? What will happen in that case? In that case, you just define a new variable, let us say x prime is equal to 1 minus x. if we define a new variable x prime is equal to 1 minus x, these boundary conditions will be reversed and they will fall back into this fixed category. Then we can directly apply the eigenvalues and eigenfunctions as the solution. I will just demonstrate whatever I am saying by a small example. For example, let us consider a two dimensional parabolic partial differential equation del u del t is equal to del square u del x square, and I will be having at x is equal to 0, we have u is equal to 0, and at x is equal to 1 we have del u del x is equal to 0. So, we just interchange the boundary conditions. So, we define an x star such as this is 1 minus x. So, del u del t does not. So, let us look into the initial the governing equation. Del u del x is equal to del u del x prime dx prime del x prime del x. So, it will be minus del u del x will be nothing but minus del u del x prime, but one more derivative, this minus minus plus. So, governing equation remains the same, del u del t is equal to del square u del x prime square. Now, when we define x prime is equal to 1 minus x, this boundary condition becomes 0. At x prime is equal to 0, del u del x prime, there is a minus sign. So, it will be cancelled out. So, it will be 0 for the basic problem, homogeneous boundary condition, and this becomes x is equal to 0 means x is equal to x prime is equal to 1. So, x prime is equal to 1, we have u is equal to 0. So, this problem is exactly fall under the category of this problem. So, the boundary condition. So, so this is our known form. So, therefore, the eigenvalues becomes 2n minus 1 pi by 2, and eigenfunctions now become eigenfunctions becomes cosine 2n minus 1 pi by 2 x prime. So, they becomes cosine 2n minus 1 pi by 2 1 minus x in the original variable. So, this will be the final form of the eigenvalues and final form of the eigenfunctions. Now, if you have a mixed boundary condition, let us look into that. Del u del t is equal to del square u del x square. So, therefore, at x is equal to 0, let us say at t equal to 0, u is equal to u naught, at t is equal to 0, u is equal to u naught, and we have at x is equal to 0, we have the mixed boundary condition, that is del u del x plus beta u is equal to 0, and at x is equal to 1, we have u is equal to 0, the Dirichlet boundary condition. Now, again we define x prime as 1 minus x. So, this becomes the governing equation remains unchanged. So, this becomes del square u del x prime square. At t is equal to 0, u is equal to u naught, at x prime is equal to, when x is equal to 0, this becomes, when x is equal to 1, this becomes x prime becomes 0. So, x prime equal to 0, u is equal to 0, and at x prime is when x is equal to 0, when x equal to 0 means x prime is equal to 1, we have minus del u del x prime plus beta u is equal to 0. So, therefore, del u del x prime minus beta u is equal to 0. Now, let us look into this, examine this problem. This again u is considered to be function of. Now, what is the difference between this boundary, this problem and the standard problem we have solved? We have solved the standard problem that the governing equation remains the same, the initial condition remains the same, the boundary condition at x prime remains the same, the boundary condition at 1 becomes the problem we have, standard problem we have solved del u del x prime plus beta u. In this case it becomes minus beta u. So, let us see how this will affect our final solution. So, it does not affect much, only a plus sign becomes a minus sign in the form of the eigenvalues, the transcendental equation that governs the eigenvalues. So, we consider u is a function of t and x. So, we will be having dt 1 over t dt dt is equal to 1 over x d square x dx square is equal to minus lambda square. So, we will be having d square x dx square plus lambda square x is equal to 0. This will be x will be x prime. So, there will be x prime. So, subject to the boundary condition at x prime is equal to 0, u capital X equal to 0, and at x prime is equal to 1, del e del x dx dx prime minus beta x should be is equal to 0. Now, the solution to this problem is x n is equal to c 1 sin lambda n x plus x prime plus c 2 cosine lambda n x prime. Now, put the boundary condition that x prime is equal to 0, x equal to 0. So, this becomes 0 is equal to c 2 cos 0 is 1, sin 0 is 0. So, c 2 equal to 0. So, x n becomes c 1 sin lambda n x prime. Now, we have the other. So, now we use the other boundary condition c 1 lambda n cosine lambda n x prime evaluated at x prime is equal to 1 minus beta x n. So, beta c 1 sin lambda n x prime evaluated at x prime is equal to 1 should be equal to 0. So, we take c 1 common. So, c 1 and this lambda n cosine lambda n minus beta sin lambda n, okay, is equal to 0. So, for c 1 not equal to 0, we have lambda n minus beta tan lambda n is equal to 0. So, this becomes instead of minus sign this becomes plus, instead of plus sign this becomes a minus sign. So, therefore, the boundary conditions these boundary conditions makes that the eigenvalues will be roots of this transcendental equation lambda n minus beta lambda n, and the eigen functions remain same as sine functions, but in this case it will be sin lambda n x prime. So, it will be in terms of x it will be c 1 sin lambda n 1 minus x. So, only that much change will be there in the governing in the solution. So, therefore, if the boundary conditions are interchanged, then you have a shift of axis and bring the boundary conditions back to the original problem, the problem that we have already defined, and you will be getting the solution straightforward with the change in the and later on in the transformed variable you convert the transformed variable into the original variable by putting x prime is equal to 1 minus x and or y prime is equal to 1 minus y, something like that. That will give you the complete control of over the all kinds of boundary conditions, whether they will be appearing on this boundary or that boundary, it absolutely does not matter. So, the method is absolutely clear to us what to do if the boundaries the boundary conditions do not appear the same way of whatever we have done this we have used for solving such problems for several classes. If the boundary conditions are interchanged, you shift the axis of the independent variable as x prime is equal to 1 minus x and redo the problem, reformulate the problem and solve the problem as earlier we have done. So, it remains the same and the method remains the same, that gives us the ability to tackle all sorts of boundary conditions appearing in anywhere in the boundaries. Next, so that finishes over the 3-dimensional parabolic 4-dimensional parabolic problem. So, it gives the most general type of parabolic problem. Now, again if some of the boundaries will be having Neumann, some of the boundary conditions will be having Robin mixed, the eigenfunctions and eigenvalues will be changed accordingly. If in a chemical engineering problem, if there are so many non-homogeneities appear. So, for this particular last problem we have solved, the 4-dimensional problem we have solved, there are 7 boundaries that we have dealt with. One boundary is the initial condition. Initial condition is basically a special type of boundary, one initial condition and 6 boundaries on 6 boundary conditions on 6 boundaries, 2 on x, 2 on y, 2 on z. Now, out of these 6 boundaries, if in a most general case that all of them are non-homogeneous in nature, then you have to define your temperature such that one of the boundary conditions will become homogeneous. So, you reduce the number of non-homogeneities from 7 to 6 and define this problem into 6 sub problems taking one non-homogeneity at a time. Out of these 6 sub problems, one problem will be well posed. Which one will be that? That will be the non-homogeneous initial condition and all 6 homogeneous boundary condition, and we have already seen how to solve that problem in this class, and you will be able to solve that problem completely. On the other hand, the other 5 problems will be having the non-homogeneity in one of the boundary conditions, but homogeneous initial conditions. So, each of these 5 problems you have to divide into 2 more sub problems. One will be the steady state part, the time varying part, another is the time independent part. The non-homogeneous part of the problem will be associated with the steady state part or time independent part that will force the corresponding boundary condition in the time varying part to be homogeneous, and the homogeneous initial condition of the time varying part will become a solution of the steady state part with a minus sign. So, therefore, the transient part becomes absolutely well posed. It will be having a non-homogeneous initial condition and all boundary conditions becomes homogeneous, and we have already seen how to tackle that problem, how to solve that problem. Likewise, we break down the other 4 sub problems into 2 parts. One is time dependent, another is a time independent. Get the solution, then add all solutions up in order to get the complete overall solution. So, that finishes the multidimensional problem in rectangular coordinate. Next, I will be and the parabolic problem. So, we have we have dealt with the parabolic partial differential equations in more detail than whatever is required for this course. So, any type of parabolic linear partial differential equations you will be getting all sorts of boundary conditions, all sorts of dimensions, 2-dimensional up to 4-dimensional, you will be able to handle those problems, or you will be able to solve this problem completely. Now, let us look into the solution of elliptical partial differential equation. Elliptic partial differential equation. We will be solving the basic problem or the well posed problem first. The well posed problem will be something like this: del square u. So, it is basically elliptical partial differential is nothing but Laplacian of u is equal to 0. First, we consider a 2-dimensional problem. So, this becomes del square u del x square plus del square u del y square is equal to 0. Now, we set up the boundary conditions. So, we have 2 boundaries on x, 2 boundaries on y. So, you will be having the y axis, this is x axis, let us say this is the rectangular system or the control volume. So, this boundary is located at x is equal to 0, this boundary is located at x is equal to 1, this boundary is located at y is equal to 0, this boundary is located at y is equal to 1. So, let us consider we are talking about a square slab, where this square slab is basically covered by the control volume, and it is denoted by this equation del square u del x square plus del square u del y square. Now, let us assume that at y is equal to 0, t the u is a constant, or in general it will be a function of x. At y is equal to 1, u is equal to 0. Let us say at x is equal to 0, u is equal to 0, at x is equal to 1, u is equal to 0. So, therefore, we have out of these 4 boundaries, the 3 boundaries are boundary conditions are homogeneous, 1 boundary condition is non-homogeneous. If we would have obtained the 4 boundary conditions to be homogeneous, then we would have got a trivial solution for this. So, 1 boundary condition has to be non-homogeneous in order to get a non-trivial solution. So, therefore, we have 1 boundary condition to be non-homogeneous and all the 3 boundary conditions to be homogeneous. Now, if we look into if we analyze the boundary conditions more closely, we will see that the boundary conditions in x, they are completely homogeneous on both the boundaries, and on the other hand the boundary conditions on y are not homogeneous in y direction. So, we can formulate a standard eigenvalue problem in the x direction only, but not in the y direction. Anyway, I will stop it. I will stop at this of this class at this point. I will take this problem up in the next class and solve this problem of the elliptic partial differential equation, and then we will be looking into the various variants of elliptic PDE, and we will be also looking into the solution of hyperbolic partial differential equation in the next class as well. Thank you very much.